Here's another example. This example concerns the vertical oscillations of a mass hanging down. So we have a ceiling, a spring, a mass, and the mass is hanging on the spring. And the vertical position of the mass is denoted by y with downward positive. That's a sign convention that we are using. And the mass has, well, the mass is m, and the stiffness of the spring is k. And let's say the rest length or the unstretched length of the spring, rest or unstretched or force-free spring length of a spring. Let's say this is equal to L naught, okay? And of course, gravity is g, acceleration due to gravity is g. So we can just say g, something like that. Just to denote that there is gravity, we are considering gravity. Okay, so here are the questions. We can assign some numbers here. Mass m is 2 kilograms, let's say. Stiffness k is 4 Newton per meter. Unstretched length is, let's say, 1 meter. And here are the questions. A, natural frequency omega n of the system. In other words, the angular frequency. Natural frequency Fn of the system. And then we are going to ask C, motion y of t of the system given some initial conditions. Let's say given y of 0 equals 2 meters and y dot of 0 equals let's say 1 meter per second. Okay, so how do we solve this problem? Notice that it's not quite in the exact same configuration as we derived the equations for. So we need to sort of re-derive or re-understand how to solve this problem. So, okay, so let's actually derive the equations of motion for this system in terms of y first. Okay. So what is that? So let's draw this again. Okay, and this is y. Let's draw the free body diagram. M, and of course we have mg downward, and we have k x upward, where x is spring stretch. Should it be spring stretch? Let's actually not call it x. Let's call it y minus L naught, which is the spring stretch. Okay, so y is the total length of the spring, and L naught is the unstretched length of the spring as given here. So y minus L naught is the stretch. from its unstretched position. Unstretched length. Okay, so that's the free body diagram. That's all it is. So what we have is we can do a sum of forces equals ma in the y direction. So we can go mg, because we are doing downward positive, mg minus ky minus L naught. And the acceleration in the downward direction is y double dot. Okay, so that's the equation of motion that we have. So, or my double dot plus ky equals, sort of rearranging. So you can bring the ky to this side. This minus L naught times k minus 1 gives a plus. So mg plus k L naught. Okay. So this is the equation. Let's call this equation 1. Okay, so recall that this equation is different from our usual equation. Our usual equation is mx double dot plus kx equal to 0, or that is the standard prototypical equation with the mass going back and forth in the horizontal direction. Here, in the vertical direction, there is this constant here that is different from 0. Okay, so how do we deal with this constant? Can we convert this equation? Can we convert this equation to the standard form mx double dot plus kx equal to 0? Let's call this equation 2, okay? So is there a transformation of variables? Can we define an x such that this becomes this? Okay, what is that thing? Okay, so let's think about it. Actually, let's first find something called the equilibrium position for this system. Okay, equilibrium value of y, or static equilibrium value of y from equation 1. Okay, so what do we mean by static equilibrium? That's the question of when, if there are no external forces on the system other than what's already here, namely gravity, what is the length y that this system will sit at? Okay, so which answers the question, what length y will the system be in static equilibrium Okay, so let's try to find that first. So what is that? We can find that by a variety of different ways. You can just balance these forces. So mg equals ky minus L naught. That gives you static equilibrium. Alternatively, you can set y double dot equal to 0 and 1. Okay. Set y double dot equal to 0 because static equilibrium means no motion or no acceleration. Okay, set in 1. So what we have is, let me just recall what 1 was. My double dot plus ky equals kl naught plus mg. And then we set this equal to 0, or y equals kl naught plus mg divided by k. So we might call this delta st or yst for static equilibrium. Okay, and that's basically L naught plus mg divided by k. Okay. equilibrium value of y. Okay, so can we understand this equation or this expression? It's quite intuitive. Okay, so L naught is the free length or the unstretched length of the spring. So so the spring will be at L naught if there is no force on it, but because M is pulling the spring down, the spring is going to stretch by mg by k, force divided by stiffness. So this is the spring stretch. This is the initial or unstretched length of the spring. So y itself, which is the total length of the spring, is going to be L naught plus mg over k. So that's basically what we have derived. It's the initial length, or not initial, the equilibrium length of the spring in the absence of any motion for the system. Okay, so that's the equilibrium length. So when we have problems where you have this external force or right-hand side not equal to 0, what you do is you first compute the static equilibrium value of y. Okay, so that's the first thing to do. And then we define x, this new quantity, which is, so define a new quantity x as y minus delta st. Okay, we define it as y minus delta st, or yst, or whatever you want to call the static equilibrium. So basically y minus L naught plus mg over k. Okay, so basically you're defining x as, note that x does not mean horizontal position anymore. It means this other thing. X is the deflection or the deviation from the equilibrium, static equilibrium position. Okay, in the classic example, in the mx double dot plus kx equals 0, the example of mass going back and forth horizontally, we had defined x as the deviation from the unstretched length of the spring, which is also the static equilibrium position of the spring there. Here we are defining it from not the unstretched length of the spring, but this quantity. Okay, we're defining x as the deviation from this y value. Okay, this y value. So in other words, we are saying in the absence of motion, the spring might be in some position because of this external force, and we are measuring x from that equilibrium position. Okay, not the unstretched length of the spring, which is L naught, but from the equilibrium position of the spring, which is different because of the external force being present, mg. Okay, so that's x. Now we can see if we can rewrite this equation in this form. So let's look at this equation again and then substitute y in terms of x. Okay, let's call this 3, let's call this 4, use, and then if you can differentiate 4, x double dot you get x double dot equals y double dot, because all these things are constants. So use 4 and 5 in 1. So we have, let's just recall 1, my double dot plus ky equals kl naught plus mg. So we can just plug in y equals x plus this thing. Y double dot is x double dot y equals x plus L naught plus mg over k equals KL naught plus mg. Let's just multiply through mx double dot plus kx plus KL naught plus k times mg over k equals KL naught plus mg. And notice that we have all these terms here that basically get cancelled, and all we are left with is mx double dot plus kx equals 0. Okay, here's the big result, which is that if you measure x from the static equilibrium position of y, then x satisfies this equation. Okay, x satisfies this equation. So what does that mean? We can now use all the tricks that we learned for x, but now apply it for y. Okay, so therefore the system has the same behavior as mass oscillating horizontally, like the original standard problem, right? So this problem, except we need to use y equals x plus L naught plus mg over k. Okay, so solve for x of t, and then y of t is just x of t plus L naught plus mg over k. Okay, more generally, step 1 is find static equilibrium. For whatever system. By setting all the dot terms to 0. And then 2, you go y of t equals delta s of t plus x of t. Okay, so this method is going to be true for whatever system. Okay, so let me just expand on that. So part A, omega n is still going to be square root of k over m, because, well, our equation is in fact basically the same as before. So we can compute that. So we did k over m, 4 over 2, which is square root of 2, like before. Hertz. I asked for the natural frequency in real time as opposed to the angular frequency. This is the angular frequency. So if you're asked this quantity, it's actually omega by n by 2 pi, which is square root of 2 by 2 pi, which is whatever that is, okay? And that's also in hertz. And then we ask for the motion y of t. Okay, so what is y of t? We just established that y of t is x of t plus the static equilibrium position, which is x of t plus L naught, which is, let me just write, L naught plus mg over k, and L naught plus, what is L naught? L naught is 1 meter, mass is 2 kilograms. So let me just compute the static equilibrium separately. So delta ST is L naught plus mg over k equals 1 plus mass is 2 kilograms, g is, let's say, 9.81, divided by k, which is 4. So 1 plus 9.81 divided by 2, whatever that is. So let's compute it. I'm using my computer to compute it. That's a 5.905 meters. Okay, so that's static equilibrium. And then we say, what is x of t? We recall the formula, which is x of t equals x naught cosine omega n t plus x naught dot by omega n sine omega n t. So that's x of t. What is given is initial conditions. If you go back up, what is given is initial conditions in terms of y, not x. You're given initial conditions in terms of y. So let's write that down. Y of 0 is 2 meters. Y dot of 0 is 1 meter per second. So y naught is 2 meters and y dot naught is 1 meter per second. If y is 2, what is x naught? X naught is, of course, y naught minus delta st. So 2 minus 5.905. And you get minus 3.905 meters. That's x naught. And then x dot naught is basically going to be y dot naught, because x naught and y naught differ only by a constant. So we just get 1 meter per second. So what we have is x of t is, sort of using just this formula, is minus 3.905 cosine square root of 2t plus 1 sine square root of 2t. That's x of t, and then y of t is this quantity plus the static equilibrium position, which is 5.905 minus 3.905 cosine square root of 2t plus 1 sine square root of 2t. So that's actually going to be the motion. So what is the meaning of this? The meaning of this is the following. So it says x of t, once you have sort of done the conversion, x of t will have some motion about 0. I'm not necessarily drawing this precisely about how it starts and so on, but so if you want to be more precise, actually, if it's going to start with negative 3, that's x equals 0 at time equals 0, x at time equals 0, and then it's got a positive velocity. So it's actually going to look like this, more like something like this, let's say, okay? Anyway, so x of t oscillates about x equals 0, and then y of t will oscillate. So let's say this is y equals 0, y of t will oscillate about, this is y equals 0, this is 5.905, which is the static equilibrium position. The oscillations are about y equals static equilibrium, in other words, okay? So let me draw a dotted line there. Okay, so that's the meaning of this offset. The spring is already hanging at some equilibrium position in the absence of any motion, and then if you pull the spring and let go or give it some initial condition, it will oscillate about that equilibrium position, not about 0. That's a pretty intuitive result overall. Okay, that's it. Let's say you're asked to find the amplitude of oscillations. Then you just go square root of this square plus this square. I didn't quite ask that, but in this case, if you say amplitude of oscillations, you just go square root of x naught square plus basically this quantity square minus this quantity plus this quantity square. So if we ask amplitude of oscillation, that's how we do it. Okay, it's the square root of sum of squares of the quantities that serve as the coefficients for cosine and the sine. Okay, so that's it. So just to be clear, we didn't ask for the amplitude of oscillation, we just asked for y of t. This is where the problem ended. But if you do ask for amplitude of oscillation, which is this extent, that's actually square root of the coefficients of cosine and sine squares. Okay, let's stop there.